This is the second section of electron configurations. And last time we were looking at using the building up principle, the Aufbau principle, to find the ground state electron configuration and being able to write those out. I'm going to start this section by doing one more example of finding an electron configuration. And to do this, I'm going to start with the period. Let's use, here's our challenge, if you will, use the building up principle to find the electron configuration. Let's do it for the atom calcium. So we're going to find the electron configuration of calcium using the building up principle. Now, I showed you last time how to do this with a periodic table. And I had forgotten to, one thing I want to show you is figure 8.12 in your textbook. Figure 8.12 shows you exactly what's going on with the building up principle. If we start here, 2s fills, the 2p fills, the 3s, the 3p, 4s, the 3d, and so on. Okay, so this can be a handy thing to refer to. Another way to find the electron configuration is to use this mnemonic from your textbook also. Some people like to use this one. I find it's easiest to simply use the periodic table and essentially know what's in this chart here to be able to use, to apply the building up principle. Okay, so let's use this to find the electron configuration of calcium. Calcium is right here in the periodic table. We know that for hydrogen, it would be 1s1, helium is 1s2. Where am I getting that from? Well, it's essentially this, right? So we're filling the 1s shell here. Okay, next we're going to find the electron configuration of up to beryllium. So that would bring us to 2s2. Remember, this section here is s orbitals. This are the p orbitals. These are the d orbitals. And then the f orbitals are the lanthanides and actinides. We won't really have to worry about those so much. Okay, so all right, so we are at 1s2, 2s2. This is 1, 2, 3, 4, and so on. So 2p6 will bring us to neon. 3s2, right, will bring us to the electronic configuration of magnesium. Then 3p6 will bring us to here, and 4s2 will bring us to calcium. So that would be the ground state electron configuration of calcium. We can see, just to check our work, here it is, the ground state electron configuration of calcium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and we've done it. So I find it's easiest to use the periodic table, and knowing what's in this figure from your text, figure 8.12, and just using the building up principle to find the electron configurations. Some people do like to use this mnemonic. It's up to you what you like to use, and do what you need to do to make sure that you know how to find the ground state electron configuration. Okay, so just remember that in the last we ended last time by talking about what ground state means. That's the lowest energy configuration. We talked about excited states and so on. We talked about some exceptions to building up principle. And so let's look now. We're going to continue on with looking at the at electron configurations. We're going to look at something called Hunds Rule. And what this is essentially what Hunds Rule says, and this is for electron configurations and and diagrams, orbital diagrams, what Hund's rule says is it just says that electrons will distribute themselves so as to give the lowest energy. Okay, and where this really comes in is with orbital diagrams, and it comes in and says that orbitals of equal energy will each contain an electron of the same spin before pairing spins in one orbital. So let's write that down. Orbitals of equal energy will each contain an electron of the same spin before pairing spins in one orbital. Okay, let's look at an example of this, an example of this to be able to see what we mean. Okay, so let's take the phosphorus atom, phosphorus 15. So to find what would the electron configuration be for phosphorus, okay, well we can use our periodic table that we had just looked at. Okay, phosphorus is right here, so it would be 1s2, 2s2, 2p6, 3s2, 3p3. Okay, so 1s2, 2s2, 2p6, 3s2, 3p3. So I got that using the same method I used to find any others, right? Knowing that these blocks, this is the S block, the P block, the D block, and so on, and phosphorus would be right here, so it would be the 3p. All right. So we have that. Now let's look at what Hund's rule is saying. So Hund's rule, you don't really maybe where it applies itself is with orbital diagrams. If we had to draw or write out the orbital diagram for phosphorus, it might look something like this. We have the 1s orbitals, the 2s orbitals, each with 2 electrons in it. Each electron has an orbital contain 2 electrons, but they have to be opposite spins, and we indicate the fact that they have opposite spins by using arrows that go up or down. You can use whatever kind of arrows you want. Okay, 2p, there are 6 electrons there. The 3s orbitals are like this, and now we come to the 3p orbitals. Okay. The 3p orbital is not going to be completely filled because we only have 3 electrons in this, right? So we have 6 electrons that would completely fill the orbital. What Hund's rule says is that orbitals of equal energy will each contain an electron of the same spin before pairing spins in one orbital. Now, the 3p orbitals are each of the same energy, and so to fill these, what we will do is we will put 1 electron of the same spin before we start to pair spins into one orbital. So you may be tempted to do something like this. 1, 2, 3. This would not be the ground state configuration. Now, is this a possible state? Well, absolutely it's possible to put 2 electrons into the same orbital at opposite spins. But what you need to do is to find the lowest energy configuration, we put 1 electron into each orbital before we start to pair them. That gives us the ground state electron configuration using Hund's rule. Okay? All right. One other topic with respect to two more topics that we have with respect to orbital electron configurations are, let's look at magnetic properties. Magnetic properties, and what we have with magnetic properties of materials is magnetic properties give us experimental evidence for unpaired electrons. So like how do we know that we have phosphorus as being something that has an electron in one in each orbital first, as opposed to pairing them up? Okay, and there are two essentially types of materials: paramagnetic materials and diamagnetic materials. Okay, paramagnetic materials are attracted by a magnetic field. Okay. And what this means is that we have unpaired electrons. There are unpaired electrons in the material. So if something is paramagnetic, that means we have unpaired electrons. Diamagnetic materials not attracted by a magnetic field, or even slightly repelled by a magnetic field. And what this means is we have no unpaired electrons in our materials. So paramagnetic, unpaired electrons; diamagnetic, no unpaired electrons. So what we can ask ourselves is, if we take, say for example, some material, let's just take silicon as an example. Silicon has 14 protons. Going back to our periodic table, it sits right here. It's next to phosphorus. Okay, so our electron configuration, I challenge you to come up with this on your own, as a little bit of practice, would be 1s2, 2s2, 2p6, 3s2, 3p2 would be the electron configuration of silicon. Now, if we draw the orbital diagram, and what I'm going to do is I'm going to draw the orbital diagram for only the valence electrons. Valence electrons, again, recall, highest n value. Electrons in the highest n value. So the highest n value for silicon is 3. So I'm going to have the 3s orbitals and the 3p orbital, 3s orbital and the 3p orbitals. It would look something like this. We're going to use Hund's rule to fill them. Opposite spin before we start to pair them. And we can ask ourselves, would silicon be diamagnetic or paramagnetic? Well, we'd expect it to be, it has unpaired electrons, so we would expect it to be paramagnetic. So oftentimes it's necessary really only to look at the valence electrons to be able to find out magnetic properties, or to apply, to figure out if something is paramagnetic or diamagnetic. All right, finally, let's look at one last topic with respect to electron configurations. Okay, so let's say we have, for example, so we all know that to form positive ions, electrons are lost from the highest n value first. So when we form an ion, a positive ion, we're of course removing electrons from that atom. We're going to remove the electron from the highest n value first. When we remove electrons, we leave the protons, and the ordering of the energies is going to be maybe slightly different than that from the building up. Well, here, let me put it this way. So we remove the electrons and we leave the protons. let's look and see what might happen with that. So for example, if we have, for example, manganese +2. Okay. If we look at where manganese is and what its electron configuration would be, we would find, let's see here. Okay, this is table 8.1. I'm just going to look for manganese. Okay, now I challenge you to find the electron configuration, write out the electron configuration of manganese by using the building up principle that I showed you a moment ago. But it would end up with, you should end up with this, which would be 1s2, 2s2, 2p6. So what I'm going to do here first is write this out for manganese first. 2p6, 3s2, 3p6, 3d5, 4s2 would be the way you'd write it out. You may be writing it in the way I just showed you if you use the building up principle. It may be the same here, 3p6, 4s2, 3d5. Okay, so that's for the manganese atom. Now, if we have the manganese +2, we remove 2 electrons. We're going to remove them from the highest n value first. What's the highest n value? Right there. Okay. Depending on which way you write it, you can write it either way. It doesn't matter to me if you write it this way, if you write it this way or this way. But if you do make the ion, you remove from the highest n value first, which is going to be the 4s electrons. So for this, we would write it 2p6, 3s2, 3p6, 3d5 would be how we would do that. And of course then for negative ions, we complete we're essentially usually completing the outermost shell. So electrons gained to complete outermost shell. So as an example, we have chlorine and chlorine minus. Let's write the electron configuration of both of those. Okay. I would encourage you to just pause this and give it a try. But what you should find for chlorine would be 1s2, 2s2, 2p6, 3s2, 3p5. That would be for the chlorine atom. We add an electron. We're completing the outermost shell. 1s2, 2s2, 2p6, 3s2, 3p6 would be the electron configuration for a negative ion. It's all we've done is we just added one more electron to the atom, and we found its electron configuration. Right.